this chapter, we will be looking at various types of functions. In this lesson, we will be looking at the composition of functions.
Okay, so in the last couple of lessons here, we've been looking at how you can use functions and apply sort of the similar rules of arithmetic that you would normally apply to variables. Okay, and they behave exactly the same as you'd expect them to behave. Addition, subtraction, multiplication, division, they all basically make sense using functions here. This next thing that we're going to look at right now, something called composition of functions, okay, is a little different, and it is an operation that is basically unique to this, to functions, okay? And the way it looks like, what it looks like is this, would be f of g of x. So in other words, where the independent variable would go inside f of x, we're replacing it with another function here, okay? So what we're going to do here is we substitute in that g of x in for f of x here. Now here's some other notation here. So f, and now we're going to use, and I'll zoom in on this because it's important you see this. F open circle g means f of g, okay? It's a composition. We're composing f with g. We could do it the other way around, compose g with f, okay? And actually we can compose a function with itself, okay? We can put a function inside itself here. Now there's some interesting things that pop up when we start to do this sort of work here, okay? A couple of words of warning here. This is not to be confused with multiplication, okay? When we have the open circle there, it does not mean the same thing as the closed circle. It is not multiplication here, okay? It's not f times g. This is f of g. You put the g inside the f function. Now it says here, to determine the equation of the composite function, substitute the second function into the first and read it from left to right here. Okay, and which makes perfect sense. You're going to plug that thing in, and you're going to try to expand it out here, do whatever simplification you need to do to get that expression as simple as possible. Now, here's another little bit that you need to know here. The domain of f of g of x is the set of values of x, okay, in the domain of g, for which g is in the domain of f. Now, okay, that's a little bit weird to follow here, but there's some steps here, there's some layers to this. We're looking for the values of x in the domain of g. Okay, so g has to be defined. But the values that g produces, okay, so the y coordinates of g have to be in the domain of f to make that work. So think of it like this, okay? If you've got, for example, let's say f of x is the square root of x, and g of x is, let's say, just x plus 2, okay? Now, if I compose these two right here, f of g of x, okay, and to get whatever here, let's talk about the domain though. G is defined for all real numbers. Okay, that's not a problem here, that's good. Okay, this is just a line here. However, when it produces positive numbers, that's the only place that I can plug that into here. Okay, so composition, maybe I do need to write this out. Composition is going to look like this. G of x is going to replace the x in my function. So this is going to be the square root of g of x. And that becomes the square root, and this is the square root of x plus 2. So my domain here is going to be where whatever's inside here is got to be positive. So my domain would be here where x is going to be greater than or equal to negative 2. So just graphically speaking, okay, here's negative 2. I'm only interested in this function here, in the domain where this function here, this x plus 2, is greater than 0. I can't let it go into quadrants 3 or 4 here. And that's basically what we're talking about when we restrict the domain here, what this is referring to. You'll often find that it's probably easier to find out what that function is first and then look for the domain here. But if you remember this little step here, we're looking for, first of all, the restrictions on g, and then we're looking for the range, basically, of g that becomes the domain of f. I know it's complicated. You're going to have to look at a few questions before that'll make perfect sense to you.
Evaluate the following composite functions where f of x is equal to 2x and g of x is equal to x squared plus 2.
Okay, so what we're doing here is we're composing g with f. So we put f of 2 in there. Now, Okay, let's look at the f function here first. We have to look at what's inside the brackets, then we got to look inside what the brackets again. I got a 2 in here, a 2 in f of x. Let's take a look here. If you plug 2 into this, the result is going to be 4. So this is the same as g of 4. And now let's go to the g function. If I plug 4 into this, 4 squared is 16, plus 2 is 18. So g at 4 is 18. So this is just a step-by-step process here. Take a look at this one. Again, work inside that set of brackets, now work inside this one. There's the number 1. Okay, that's 1 inside f of x. Now, if I plug a 1 into f of x, that's going to be 2 times 1, which is just 2. So this will be g of 2. Go over to g. If I plug 2 into that, 2 squared is 4, plus 2 is 6. So g at 2 is 6. Okay. Over here, g at f of 0. Okay, well, f of 0, if I plug 0 into f, well, I'm just going to get 0. So this is going to be the same as g of 0. F of 0 is 0. And then g of 0, if I plug 0 in for x, 0 squared plus 2 is just going to be 2.
If f of x is equal to 4x and g of x is equal to x plus 6 and h of x is equal to x squared, determine the following and simplify all answers.
Okay, so this question is more algebraic in nature than the previous one here. So we're going to compose f of g here. So this is going to be the same as f of g of x. Okay, now g of x, we can look up here, is going to be x plus 6. That means I can replace g of x in this function here with x plus 6. Now, what does f do? Well, the function f here takes and multiplies the independent variable, whatever's inside the parentheses here, by 4. So what this is going to do here is this is going to take, f is going to take 4 and multiply it by x plus 6 to get 4x plus 24. X plus 6 is really now the, if you want to think of it like this is the independent, the independent variable in f, and the rule is multiply the independent variable by 4. There we go. Okay, now let's take a quick look at this. What happens when you change order here? So this is the same, f of x was 4x. So I'm going to replace f of x inside here with 4x. Okay, that's exactly what f of x is. Now, what does g of x do? Well, g of x takes the independent variable and adds 6 to it. In this case right here, the independent variable has been replaced with 4x. So g is going to take 4x and add 6 to it. Now that's really interesting here because notice that when I change the order of composition, it changes the function here. This is not, they're not the same thing, okay? So composition, I've lost the word here when you switch, when you switch the order here. Anyway, for some reason I've lost the word here, it starts with a C. But when you switch order, you're getting 2 different results here. Now that's not the same as, for example, multiplication and addition, where if you switch the order, it doesn't change the result here, okay? G can be composed with itself. Now g of x is x plus 6. This is going to be the same as g of x plus 6. Now this whole thing here becomes the independent variable for g. G adds 6 to the independent variable. So this is going to be x plus 6 plus 6. Okay, so this is the independent variable. I take that, add 6, and I'm going to get x plus 12 as my result. Okay, down here, f of f, so this is f composed with f. F of x on the inside here, f of x all by itself is just this nice little clean x 4x. Okay, now we got to think, what does f do? Well, f takes the independent variable, whatever's inside, multiplies it by 4. In this expression here, okay, the independent variable is 4x. So f, this function here, is going to multiply that by 4. And so my result is going to be 16x. Now, we haven't used h yet. So g of h of x. Now, h of x, if we look back up here, h of x is x squared. So this is going to be g of, I can simply replace h of x with x squared. That's what it is. Okay? Now, g takes the independent variable, whatever's inside those parentheses is the independent variable, and g adds 6 to it. So this is going to become x squared plus 6. Okay, and now you can do the same thing with 3 functions. You can compose 3 of them, okay, themselves here. Now, I already know what g of f of x is, okay, but we'll do this kind of slowly anyway. So I'm going to work with on the inside out here. I know that f of x is 4x. I'm going to replace f of x with 4x, okay? That's exactly what it is. Boom, done. Now, what does g do? Well, g takes the independent variable and adds 6 to it. In this case, the independent variable is 4x. So it's going to add 6 to this, but that all happens now within the h function. So this will be 4x plus 6 inside the h function. And now, what does h do to the independent variable? Well, what we just saw here was h squares the independent variable. So this is going to end up becoming 4x plus 6, the independent variable, the whole thing squared. And when we square that, okay, we've got to FOIL that out here, we're going to get 16x squared plus 48x plus 36. There we go. It's just a matter of doing this in the correct order and making sure that when you apply the rule to the whole expression that is now within the other expression here. So just again to reiterate that, look over here. When I plug g of x into this, I'm going to multiply, f tells me to multiply whatever the independent variable is by 4. You got to make sure you multiply the whole thing, just that you're applying the rules correctly, that you're distributing over binomials and so on. Just be careful with your algebra.
Determine f of g of x and g of f of x for each of the following, then determine the restrictions on the variable for both composite functions. F of x is the square root of x, and g of x is 2x minus 3.
Okay, so here, what we're going to try to demonstrate here is that order does matter here. And the word I was looking for before was commutative. Okay, when you change the order here, you actually change the function here. We're going to demonstrate that with a few examples here. Composition is not commutative. Can't believe I forgot that. Anyway, so here we're going to start off with f of g of x. Okay, well, g of x can be replaced immediately with 2x minus 3. So this is going to be f of 2x minus 3. Now, what does f do to its independent variable? Well, it takes the independent variable and finds the square root of it. So this is going to end up being the square root, and in this case, the independent variable is 2x minus 3. I know people want to think that the independent variable is just a single letter, but in this case, it's just not behaving like that. This whole thing is my independent variable here, okay? And then this becomes 2x minus 3. Now, if it kind of helps you think about it here, then what we would do here is we might relabel this as h of x, in which case now we would identify the x itself as just the independent variable. But at this point right here, now you got to think of it more as this whole thing. That 2x minus 3, that binomial, is acting like the independent variable here. Now let's change the order. So this will be g of f of x. Okay, in this case here, f of x is the square root of x. So this will be g of the square root of x. And now what does g do to its independent variable? Well, g multiplies the independent variable by 2 and then subtracts 3. So 2 times, in this case, the independent variable is going to be root x minus 3. Okay, let's call this k of x. Okay, now notice, again, that depending on the order, okay, you get a different result here. So f of g of x is the square root of 2x minus 3, whereas g of f of x is 2 root x minus 3. They are not the same. All right, now let's take a quick look at the restrictions here. So for this first one, okay, what's going on here is 2x minus 3 has got to be greater than or equal to 0, okay, because they're all inside the square root there, so 2x has to be greater than or equal to 3. And so now if we bring the 3 over, we'll get 2x has to be greater than 3, and then divide by 2. X has to be greater than or equal to 3 halves. So there's the restriction on h there. On k, it's not quite as restrictive there, because it's just the radical here that I'm left with, radical of x there, and I know that when you have got the radical like that, whatever's underneath the radical there, whatever the radicand is, has to be greater than or equal to 0. So there's the restriction for k. Doesn't require quite as much work in that case.
F of x is the square root of x minus 1, and g of x is x squared.
All right, let's just do this again. Remember, first we're going to start by composing f with g. We know that g of x is x squared, so this will be f of x squared. I can just make a straight replacement for g of x. And then what does f do? Well, f takes its independent variable, subtracts 1 from it, and then square roots the whole thing. Well, in this case, the independent variable is this x squared. Okay, it's a little bit more complicated than just a variable here. So I'm going to take x squared minus 1 from that, and then square root the whole thing. And again, if I want to have this, or rewrite this in a way that where the independent variable makes more sense to me, I can just introduce a name here, call it h of x, and there we go. So h of x is the composition of those two. Switch the order, g of f of x. I can directly substitute f with the square root of x minus 1. And then g, remember g squares its independent variable. Now in this case, that's the square root of x minus 1. And when you square that, we're simply going to lose the square root. So this will become x minus 1. And we maybe call that k of x. And those are very, very different. Okay? So again, order makes a big difference here. All right. Now let's take a quick look at the restrictions. So here, we know that x squared minus 1 has to be greater than or equal to 0. And when we bring that over, we get that x squared must be greater than or equal to 1. Now, this is going to occur in two different directions here, okay? Either x is going to be less than or equal to negative 1, okay? Or x is going to be greater than or equal to positive 1. In both of these directions here, x squared will be greater than or equal to 1, okay? So just think about it like this. If you choose like negative 2 squared is positive 4, that is greater than 1. Okay, if x is equal to positive 2 squared again is 4, which is greater than 1. So both of those work there. This is the restriction there. Now here, it might look like, well, this is just a linear function. It has no restrictions. Okay, and there's a little bit of truth to that. However, we have to kind of go around a square root to get to that point. Okay, now granted, g takes what's inside and squares it, but there is a restriction here that comes with this radical before we get to the square here. Okay, even before we start to that, right from this point right here, there is a restriction that x minus 1 has to be greater than or equal to 0, which means x has to be greater than or equal to 1. This function right here is restricted right from the beginning. Even though the square root eliminates that, we're still stuck with the fact that x has to be greater than or equal to 1 here. Okay, that restriction from the beginning has to carry through to the end. Okay, it's not possible for this to be defined everywhere, even when one of the pieces of the composition isn't. So the restriction has to be that x is greater than or equal to 1.
F of x is 1 over x minus 1, and g of x is x squared plus 2x.
Okay, one last time here. F of g of x. And I will substitute right away. G of x is going to be x squared plus 2x. So this expression here takes the place of the independent variable in f. And now what does f do to its independent variable? Well, it subtracts 1 from it and then makes it the denominator of 1. Okay, I have a fraction where 1 is in the numerator. So this is going to end up being 1 over the independent variable and then minus 1. So this whole thing, x squared plus 2x minus 1. Okay. Now, and again, just like I've done before, I could call that h of x if I needed to, if that kind of helps me get my head wrapped around how the variable gets named here, it gets utilized. Now let's change order. G of f of x. Okay, well, f of x is 1 over x minus 1. Now what does g do? Okay, well, g squares its independent variable and then adds 2 times the independent variable. Now in this case, we've got this expression right there for that independent variable. So this is going to be 1 over x minus 1 squared plus 2 times 1 over x minus 1. Okay, well, I'm going to need a little bit more room here. Okay, so this is going to be 1 over essentially x minus 1 squared plus 2 over x minus 1. Okay, I'm going to have a common denominator of x minus 1 squared, means I got to multiply this by x minus 1. And that's going to get me 1 plus 2 times x minus 1 all over x minus 1 squared. All right, that's going to be 2x. Okay, when I multiply that through, now I'm going to get negative 2 here, so 1 minus 2 minus 1, okay, x minus 1 squared. And if I feel comfortable, or if I need to do this, I can call that k of x here now. And again, notice that it makes a big difference. Order makes a huge difference. Now, it doesn't have to make a difference. I should probably not kind of lead you down that road here. It is possible that you can compose a function with another function and order doesn't matter. It's just that oftentimes, frequently, order will matter. All right, now let's have a look at the restrictions for this one. For h here, this first one, it's going to be where the denominator goes to 0. Can't let that happen. So x squared plus 2x minus 1 equal to 0 here. Probably going to have to pull out the quadratic formula, so it'll be negative 2 plus or minus the square root of 4 minus 4 times a times c, negative 1, all over 2 times a, 2. And that is going to equal, sorry, and x can't equal this, but this is going to equal, what is that going to be? Negative 2 plus or minus, well, that's going to be 8. So 2 root 2 all over 2. And so that's going to equal, divide everything through, it would be negative 1 plus or minus root 2. There's my restriction. Okay, x cannot equal negative 1 plus or minus root 2, or this thing becomes undefined. Let's look at the second function here, k. In this case, it's a lot simpler here. It's just that x minus 1 squared. It's already in factored form, so I know that here that x cannot equal positive 1. Okay, and again, just illustrating that the fact that when you change the order of composition, you're going to change the function, you change the restrictions.
If h of x is equal to f of g of x, determine f of x and g of x.
Okay, this is an interesting question here. We're told that h is the composition of f and g here. Okay, and now we're supposed to take a look at h here and basically decompose it back into f and g here. Now, this actually is up to a little bit of interpretation here. This one I think is quite clear what they want you to do with this. Remember that g is inside f. G takes the place of the x inside the f function here. Now just take a quick look at this. I think it's probably clear here that g of x is very likely 3x minus 1. That particular expression is repeated. Okay, so you could think of it as this must be where the x was, this is where the x was, and then g is taking its place, which means f of x is very likely x to the 4th plus x squared plus 1. I think that's the most straightforward reading of this particular question here. But compare that with this next one. H of x is equal to the square root of x cubed plus 1 here. Well, I could interpret it like this. Well, it looks to me like what you've got here is g, the inside function, could be interpreted as x cubed plus 1, where f of x is the square root of x. And then g, once again, is composed inside, with f there, or f is composed with g, that goes into where the independent variable is. And that works here. Or you could interpret that as g of x, for example, is equal to x cubed, and f of x is equal to the square root of x plus 1. And then when I compose f with g here, okay, when I put the x cubed inside f, it's going to replace the x here. Now, I just show you these two options here, and I'm not going to go much further than this, but just to show you that there is a little bit of interpretation here, okay? As long as what you're doing is correct, or at least leads to a correct composition, you should be fine in how you decompose that into those two original functions.
Use the graphs of f of x and g of x below to evaluate the following.
Okay, so now we're going to use this graph here to work through function composition. Once again, the trick is to remember which function is which here. So g of x is the radical function here, and it looks like f of x is the absolute value. So f of g of negative 4, so first of all, is going to be f of, well, g at negative 4. G at negative 4 is 1, so this is the same as f of 1. F of 1 is 2. So f of g of negative 4 is going to be 2. You just bit at a time here, start on the inside, work your way out here. So for this case right here, f of g of negative 1, So first of all, let's look at where negative 1 is. G at negative 1 is going to give me 2. So this is going to be the same as f of 2. 2 is over here. F of 2 along that absolute value is going to be 1. Now we switch order here. Again, start on the inside though, negative 1. So we're starting at negative 1 here. F of negative 1 is 4. So this will be the same as G of 4. Then I go over to where to 4 here and go up to G, and I get 3. G of 4 is 3. So G of f of negative 1 is 3. F of G of 4, okay, I start at 4, and I'm going to go to G, and that's going to give me 3. So this is the same as f of 3. Go to 3, and then f of 3, well, that's right on the x-axis, so that's going to be 0. Okay, that's how you compose these things. Just one step at a time. Don't try to do too much too quickly. One step at a time. Start at the middle, identify where that value is, identify the value of the inside function, and then that becomes the x-coordinate for the outside function.
Use the graphs of g of x and f of x below to evaluate the following.
Okay, so this question is very similar to the previous one. Again, we just need to identify which is the f function, it's the absolute value here, and then g is this linear function here. So to evaluate these guys, we start first of all in the middle, negative 4. So we come across here at negative 4, and g at negative 4 is 0. Okay, so that becomes our inside value, okay, the independent variable of f. F at 0 is going to be 2. We just walk that through. Now again, we go to the inside term there, we get 0, 0, g at 0 is negative 4, so this becomes f at negative 4, and then we follow negative 4 back, go up to f, and we get a y value of 2. Good. Now we switch it a little bit here. We start at negative 2, and we do f at negative 2. Well, f at negative 2 is 0, so this is going to be g at 0, and g at 0 is going to be negative 4. Next one says we go to negative 3, so negative 3, we go f evaluated negative 3 is going to be 1, so this will be g at 1, okay, and g at 1 is 3. F at negative 4, we go back to negative 4, f at negative 4 is 2, so this becomes g at 2, and g at 2, come down here, all the way down there, is going to be negative 6. Good. That's what we're looking at. I just want to double check that I got this one right here. Yeah. G at 1. Oh, hold it. I got G at 1 there. I knew I had messed that up. My mind wandered there for a second. I'm going to go back into D here. Negative 3. F at negative 3 is going to be 1, so G at 1. Now G at 1, that's down here, is going to be negative 5. Okay? And that's what should have happened there. Sorry, I did that F twice there. Anyway, negative 5.
Given that f of x is the square root of x minus 3, and g of x is 2x squared, and h of x is 3x plus 2, write simplified expressions for the following.
All right. So here we go. We're going to compose these two functions right here, and remember that this means the same as this, f at g. G we can replace immediately with 2x squared, because we can see in the expression that that's what g represents here. And now what is f doing to its independent variable? Well, we're going to subtract 3 from it and then find the square root of that. And so this is going to be the square root of the independent variable minus 3. Okay, that's the simplified function that we're looking for here. Now move over here, we change the order. Now it should already be sort of an expectation here that this is probably not going to be the same thing here. In this case right here, we're going to replace f immediately with the square root of x minus 3. And now let's see, what does g do to its independent variable? Well, it squares it and then multiplies by 2. So we're going to take that independent variable, whatever's inside the parentheses here, we're going to square it, and then we're going to multiply by 2. Now, when you square that, that's just going to remove the square root, and we get 2 times x minus 3, or 2x minus 6 when we distribute that through. Now, finally, here we've got 3 functions composed with each other here. So this will be g of f. Now I'm going to move to the inside function here, which is h. And I know that h is 3x plus 2. Okay? Now, f, remember what f does. F takes whatever its independent variable is, subtracts 3 from it, and square roots it. So this is going to be g of, well, okay, f is going to do this. It's going to take the square root. It's going to take whatever's inside here, 3x plus 2. It's going to subtract 3 from it. And then after that, the square root applies here. Now let's simplify that. Okay, if I drop the parentheses here, I'm going to get 3x plus 2 minus 3. So that'll be the square root of 3x minus 1. And now what does g do? Well, g is going to take whatever is inside there, whatever its independent variable is, it's going to square it and then multiply by 2. So it's going to take that 3x minus 1, it's going to square it and then multiply by 2. Well, squaring is just going to remove the square root, and then multiplying by 2, we'll get 6x minus 2. So that is ultimately what this guy simplifies down to.
Given that f of x is the square root of x plus 1, and g of x is x minus 4, sketch the graph of each of the following and state the domain and range using interval notation.
Okay, well, the easiest way to go about putting this, or getting a sketch of this, is to see what this composed function is going to look like, and take advantage of any function there that I'm familiar with. Okay, so I know I'm composing f with g here, so I'm going to put g inside f, which will be f of x minus 4. There's g, just direct substitution. And what f does is it takes whatever's inside, whatever the independent variable is, it adds 1 to it and then square roots. And so what I'm going to get here is I'm going to add 1 to this. X minus 4 plus 1 will be x minus 3, and then I take the square root of that. So this is what I'm sketching here. Now, the beautiful thing about this is I already know what root x should look like. Okay, root x should start here, goes to here. It's this nice little radical function, looks like that here. Well, think about what this is doing here. Think about it in terms of transformations. This is transforming this 3 to the right. So now I'm going to start here. Okay, I'll move 1 over, 1 up. Okay, and then 1, 2, 3, 4 over, go 2 up here. So this whole function here is now moved 3 to the right. Okay, that's what that would look like. Notice that the domain and range, of x minus 4 here, domain and range are both all reals here. For this one right here, the domain is that x has got to be greater than -1, greater than or equal to -1. So the domain of the resultant function here is a little bit more complicated. It's not a direct result of those guys. At least it's not like obviously putting those together. It's not like it shares one of the domains there. It's basically it's the one transformed over here. So my domain of this final result here in interval notation is going to be 3 out to infinity. The range is going to be 0 out to infinity. Does it fairly slowly, but it does go out to infinity there. Now, for this guy over here, g of f of x, okay, all we're doing is changing the order in which we're putting the functions here. But remember, that does make a difference here. So f of x is the square root of x plus 1. And remember what g does. Okay, g takes this thing right here, takes the independent variable and subtracts 4 from it. So it's going to be the square root of x plus 1 minus 4. Now, I already know basically what this should look like here. I know what the square root of x should look like. It should start here. This goes 1 over 1 up, over to 4 over 2 up. It looks like this. What transformations have I applied here? Well, I've moved it 1 to the right. Sorry, 1 to the left. For just a brief second there, I thought I screwed up the other one here. No, this is 1 to the left, my mistake, 1 to the left, and 4 down. So that's going to take this point right here, move it 1 to the left, and then 1, 2, 3, 4 down. So it's going to go right to here. But the general shape hasn't changed because there's been no stretches here. So I would go 1 over, 1 up, 1, 2, 3, 4 over, 2 up, and so on. And so the graph's going to look something like that. Okay, there's my new graph there. My domain is going to start at -1 and go out to infinity. My range is going to start at -4 and go out to infinity. Square brackets on both of those, okay, because we are including those endpoints.
Use the table below to determine the following.
All right, so we're going to end with just using a table of values here to determine a composition of functions. So this first one here looks like this. This is f of g of 1. So we're going to work our way out. G of 1. So here's g. This is the g row here. G of 1, when x is 1, g is 4. So this is going to be the same as the f of 4. So I go to my table, I go over to where x is 4, where the input is 4, f of 4 is 2. So this is going to equal 2. Don't know what just happened out there. I'm going to assume everybody's okay. Over here, g at f of 2, this is g of f of 2. So I start on the inside there with f. I look at where x is equal to 2, and that's -1. So f of 2 is -1. Now, -1 is the input for g, and I see that that value there must be 6. Finally, over here, this is the same as g of f of -1. Okay, so I go to my chart here, f of -1. Well, here we go, -1 f, the answer there is 1. So that first little bit here becomes 1. So this is g of this little bit here became 1. Now I look at what g does when it's got an input of 1 there. So 1 g gets me 4. So this g at 1 is 4. Now I go back and I look at when the input is 4, what does the value of g become? 3. So my final answer here is 3. Now, granted, the more you nest with these functions, the longer it takes, but I don't think that the procedure is that much more difficult. It's just a couple more steps that you have to wander through.